So in this video, we're going to see how we can actually use that vector product that we defined in the previous video in order to compute the moment of a force about a point. So if you notice the definition in your book, if you wish to compute the moment of force F about point O, you need two vectors. First and foremost, you need a position vector from point O, and this is a very key point, to any point along the line of action of that force. So clearly, one of the points that you could use along the line of action is the actual point of application of the force, or the actual base of the force vector. So this is certainly a valid position vector that you could use in order to compute the moment of force F about the origin. However, technically, you can use any position vector as long as it starts at the origin and goes along or goes to the line of action of this force. Now, what happens in actual problems in the textbook is oftentimes it's hard to find an expression for another point along the line of action of the force. However, generally speaking, if you can choose a vector, if you can choose a position vector from your point of reference to the line of action that's as simple as possible, it will oftentimes make the computation of this cross product easier. So let's actually look at an example of that here. In this example, we have a force that's applied on this pipe assembly at point B. That force is actually associated with a tensile force applied by the cable. So its line of action is really easy to see. It goes from B to C along the actual cable. And what we're asked is, how many different position vectors could we use in order to compute the moment of this force about the origin? Well, what does that position vector have to satisfy? It has to start at the origin, and it has to go to some point along the line of action of this force. So it could go directly to point B. That's where the force is actually applied. However, it could also go to any point along this cable, because remember that when you have a force exerted by a cable, its direction is along the actual cable itself. That's where the line of action of the force is. So with respect to the points that we have labeled in this geometry, the position vector needed to compute the moment can go from the origin to B, or it can go from the origin to C. So let's actually look at the list. And I'm going to start out here to the right. Why aren't the points RAB and RAC possible position vectors to use to compute a moment about point O? Well, remember that position vector, there's a little bit of flexibility where it ends, but it has to start at the point about which you're computing the moment. So since we're computing the moment about point O, our position vectors have to start at point O. So naturally, we can exclude RAB and RAC because they start at A, not at O. So these three could be candidates. Let's look at them in more detail. The first one, could we use a position vector from O to A? Well, we can't do that, right? Because if you think about it, O to A is not along the line of action of this force. The force is directed along the line of action defined by the cable. The 2 points of reference along that cable on our diagram are B and C. So we can use ROB, which is the second option. We can use ROC, which is the third option. However, we can't use that for first option, and we can't use the last two. So there are two possibilities in this list that we could use. Let's look at this last example. We have a force that is applied to this block at point B, and we're asked to describe the direction of the moment of the 40 Newton force about point E using component level analysis. Now, what they actually mean by that is you clearly can't actually compute what the magnitude of the moment of that force about point E is. Why? Well, you actually have the magnitude of the force. However, you don't actually have physical dimensions of this block. So what I'm going to do, and I'm going to do a really bad drawing on my .cam here, and you're going to laugh at me, but that's okay. Let me get it drawn here. I got a little bit of a hidden line here. Sorry, I didn't actually show all my hidden lines, and I know you can't see it yet. But I'm going to define this as the depth of the block. This is the width of the block. And this is the height of the block. Okay, let me go over to my .cam, and I'll show that 40 Newton force applied at point B. So before we get started, let me ask you a question. When you're computing the moment of that 40 Newton force about point E, should you necessarily use a position vector from point E to point B? Well, clearly, if you went to point B, that would be a valid choice because it's along the line of action of that force, since it's the actual point of application. However, an easier approach, if you're computing the moment about this point, would just be to go to point G. And why would that be? Well, if you go to point G, right, that actual displacement of the position vector, it will have, and I should have drawn in the actual coordinate system to be consistent with what they had. And let me just see which convention they used, X, Y, Z. So if you go from point E to point G, you have a negative x displacement and a positive y displacement. Versus if you go to B, you have both of those, but you also have a z actual displacement. So when you're computing the actual cross product, it'll be simpler if your position vector only has two components. So what I'm going to do is I'm going to say I'll use REG versus REB due to simplicity. So let's actually see how this actually would look. So I will define the moment about point E of that force as REG, the simpler position vector from the point of reference to the line of action, cross the actual force. Can I write an expression for the force from what I'm given? Well, definitely, right? That force is actually going to have no x component, no y component, and it happens to be negative 40 for a z component, but the key point is it has a negative z component. Now, for REG, we're not going to be able to actually write an actual expression for this position vector because it is we're not given the dimensions, but using these definitions that I use, calling that dimension the depth and calling that dimension the width, in the actual x direction, it'll be minus d, and in the y direction, it'll be plus y, and there will be no z displacement to go from E to G because they're both in the xy plane. So let's actually look what this cross product would look like. And we can't do the math, but let's just arrange our actual 3x3 determinant matrix. We put the basis vectors in the first row, I hat, j hat, k hat. Then we will put the components of our position vectors, minus d, w, 0. Then we'll put the components of our force vectors, 0, 0, minus 40. Now let's actually just see what would happen if we do the determinant. When we compute what would be the I component of that moment, notice in this case, are we going to get an actual answer? Yeah, it's going to be w times minus 40 and then minus 0. So that's okay. So what I will say is you will have an I component. And the reason I will have an I component is if I cover the row and column associated with I, the resulting determinant is not 0. What about a j component? So let's cover that second column and first row. If you take that determinant, are you going to get 0? Yeah, you're definitely going to get 0. On the downward diagonal, wait, let me actually rephrase that. My D looks like a 0. Sorry, that is a D. That is not a 0. Don't make that same mistake as me. So when you cover the second column in the first row, notice that in that case, you will have a non-zero downward product. Minus D times minus 40 is some number. It's just 40D. You don't have an upward diagonal product, but that does mean you will have a j hat component as well. And what about the k hat component? Well, if you cover those actual things, now notice for this determinant, minus d times 0, minus 0 times w, both the downward diagonal and the upward diagonal product are 0. So you will not have a k hat component. So in terms of the actual answer to this problem, we will say the moment vector will have two components. And those components are an I hat component and a j hat component. So hopefully that made sense to you. Sorry for my little bit of confusion about the mistaking my D for a 0, but I think hopefully that was pretty clear to you. And I think for the next video, it's actually an example problem video. I'm going to use a recording that I had from the last semester. So if it looks like I am not looking the same, that's because it was taken back in the spring. So that'll allow me to kind of focus some time on actually doing some new examples for you, which will probably get posted maybe tomorrow or over the weekend. So we still have a little more content to do this week as well, but just note that the next video is going to be an older video.